Hello everyone, and welcome back to Day 2 of Advances in Battery Research 2025. My name is George Hammond, Senior Conference Producer at Technology Networks, and I'm pleased to welcome our opening presenter for today, Dr. Boryann Liaw, presenting his talk, AI in Battery Systems Applications. Dr. Liaw has 4 decades of experience in electrochemical energy conversion and storage R&D. He received his PhD in Materials Science and Engineering from Stanford University in 1988. He was a Directorate Fellow and Department Manager at Idaho National Laboratory during 2016 to 2023. He has served as consultant for private companies and advisors for research institutions since 1996 when he started HPRL. Please join me in welcoming Dr. Liaw. Following the presentation, we will also have a Q&A session, and we welcome any questions that you may have. Please ask questions using the Q&A system to the right-hand side of the video player. And now, without further ado, I would like to hand over to Dr. Liaw to begin his presentation.
Thank you, George. Hi, everyone. I'm going to talk about AI in battery system applications. I would like to mention that Professor Boryann Liaw from Aachen has given a fantastic talk yesterday, covering a lot of cell evaluation testing as well as some of the AI applications in the test procedures in terms of how to get the right data, how to validate them, and also do analysis with some AI techniques and machine learning approaches. I hope my talk today will be a good complement to his talk. I'm going to discuss some broader aspect of the data application, as well as some of the issues and challenges that haven't been discussed in his talk. And I hope that will be enough to share and to inspire the people in the audience about what AI's prospect could be and what the hidden problems we are facing today. So let me go to the first slide. I think the data driven approach covered a very broad aspect of the data flow. And the playing field actually start from the field data all the way to the laboratory testing. And I think the connection between the two haven't been well discussed so far in both in the literature and presentations. And I think that I'm going to comment more on this aspect. In terms of field testing, the difficulty in getting the time series data collected properly, as well as how to analyze that kind of random uncontrolled conditions. And those data can be meaningful through certain analysis, so we understand how those data reflect the real life situation versus what is being conducted through the testing in the laboratory, and how these two sets of information can go hand in hand to help each other to understand better about the battery performance, the battery technology, advantage and shortfalls, as well as how to manage the battery through the application. And so their longevity, their reliability and safety can be well under control. And so this is the playing field we're talking about. And I think a lot of complexity involved in reflecting the data and its physical meanings has been the great challenges to many people working in this area. And so I would start with this. I think the difficulty in getting the data and analyze through a real life situation hasn't been resolved today. I think that there's still a lot of gaps in the knowledge that we haven't developed sophisticated enough to reflect the connection with the laboratory test results. And that's why the simulation tools, no matter is a physics-based model or is a data-driven approach, try to fill the gap. But the gap is pretty wide, and I think the difficulties, I hope I can explain well enough through my presentation today. So the next slide, I want to show is really how to connect the human behavior and the systems that provide the service. And so we understand on the energy and the power balance between the demand and the supply. The demand side is caused by the human behavior for the desire of getting the power to support the functionality of the system to enable certain functions that human wants. The duty cycle is the system response to provide in answer to the demand. And so how to get the field test data useful can reflect the demand side hasn't been a very enabling techniques that we have today to enable all the AI applications. Here I want to show this. Back in the 90s, we already did some driving cycle and duty cycle analysis using fuzzy logic pattern recognition techniques. And so we can begin to quantify all the drivings in the sense how we can quantify their fluctuations, as well as how the system, so-called the duty cycles, responds to that kind of demand. Okay, so this has been a gap, I believe, in today's technology that we haven't been fully explored enough to get the clarity about those demand and supply issues. And what is important about that is if we don't understand the usage of the system, we probably cannot do a proper evaluation of the system in the laboratory neither. And so I think how to assess the component and system performance in the real life is very important in the future. Another aspect is how to quantify such capability in terms of how the system responds to the demands for the functionality. I think the input and output has to be able to be quantified. And we also need to be able to classify those intensity of the demand and supply. And so we can develop some numerical relationships to understand their correspondence. And so the traditional physical model use a lot of model parameterization techniques to understand how to get quantitative results. And I think that back then, because the complexity of the system is difficult to understand, I think using fuzzy logic pattern recognition techniques has been a very interesting implications in that regards. And that, just simply using the vehicle speed versus distance relationship, we can also reflect into the power versus energy consumption in response and try to develop a very useful relationship between the two become very interesting in the pursuit. So I think that people still wondering why we need that kind of experience. And I think that that's very important is without that kind of understanding, we really cannot rationalize how we can do a proper evaluation of the system. Okay, so no matter is a regulatory requirement or is a system development technology development strategy, I think that those are very necessary in order to understand whether the test result is relevant to the application itself. And that's why back in the 90s, there was a significant effort to try to define such a relationship. But evaluate any kind of driving cycle wouldn't be trivial because, the trip never being reproduced exactly over time. And so every trip is unique, and how to analyze the trip in terms of the demand versus all the duty cycles that in response to that trip demand become very complicated. And therefore, whether just using statistical analysis can fill the gap, I don't think is sufficient enough. And so back then, Idaho National Lab has been chartered to develop so-called standardized test protocols in order to evaluate batteries and their performance. And I think this is a very important aspect that we're still lacking the clarity today to make a very strong connection between the two. On the other hand, I think the laboratory testing is valuable, but those need to be conducted under appropriate test protocols and schedules. And those protocol schedules have to come back from a representative usage schedules that we learn from the real life. And so those are the interaction between the two makes sense whether the laboratory testing is relevant and useful. But most of the time we understand the laboratory testing and we know how to use design of experiment to develop metrics for the test conditions. And we can get a lot of data in terms of their dependence. But I think at the end of the day, we found the battery degradation and performance is actually quite depend on the path, which means the so-called the driving cycle or the usage will create significant impact and deviations from the anticipation of the results that we can validate through laboratory testing. And this what we call, no matter is the rate dependence, temperature dependent, or it's environmental dependent, those dependence still very complicated today to understand the intricacy between those dependence versus the response. And I think that this is the part that AI could be very helpful in clarifying. The next slide is to feel the ability to understand those relationships. I think traditionally we've been using a lot of modeling and simulation platforms in order to create that relationship. And so no matter it's the physics-based models that we know today, or through equivalent circuit models, that's more useful for a lot of electrical engineers and automotive engineers to understand in a very simple way how to emulate the battery performance as electrical components in the equivalent circuit diagrams, and so we can easily quantify their relationship and parameters become very useful for engineering purpose. On the other hand, going back to this physics-based model to understand the underlying physical process involved is also very important in the battery design. And so those two usually has to be go hand in hand. But today we using data-driven approaches, I think is making that relationship even more complicated in the sense that whether the algorithm can reflect the reality that we can understand through the physics based theater. It's still the questions that we need to answer in the future. And going through that, we talk about from cell performance to a system level performance. I think that there's many other issues that we need to deal with, such as cell to cell variations, and also the pack topology, how that's going to impact the system performance, as well as how this interaction in the distribution of the power and energy balance. We have to have more flexibility to accommodate those variations. And so using probabilistic approaches become very useful, which is really the basis for the data-driven approach. With that, I think that you can begin to see the complexity from a simple battery model based on cell performance to the whole system integration. There's additional complexity involved, which is very difficult to understand and validate. But to integrate the knowledge to the system level, there's another complexity involved, which is the battery aging and degradation. Those are the nightmares for all the laboratory testing because you cannot really define the system performance just based on a new cells that are being evaluated properly under a standard test protocols. You have to follow their aging and degradation. And those aging and degradation usually is very complicated. It's multi-scale, as well as multi-model, as well as multifactorial. And so the complexity involved in the relationship of aging versus performance is very complicated, particularly from cell to the system level. I think the complexity involved is really hard to get the clarity that we can manage today. And so whether the AI approach can solve that problem, I think we still struggle very hard today. And I think that Professor Lee yesterday has explained that as well in the cell level to the system integration and how the sensory and all the test protocol can create impact on the performance. He also has his input there regarding that aspect. And I think the most important thing is if we look the diagnostics and prognostics, we not only have to emulate the phenomenological aspect in the variations, but we also have to understand the change in the underlying mechanism that create those variations. And so those aspects is really the barrier we have today in terms of conducting proper diagnostic and prognostics in order to help the battery management system more functionally in the way that can reflect in the real time basis. Is very difficult. And so-called the in the loop simulations, which means you integrate the hardware and the software and try to train and gain data and experiences is critical. But the question is whether that can really solve the challenges we have in the AI applications. Still wait to be verified. And those aspects, I think, have been summarized 15 years ago when I finished the first 2 decades of efforts in understanding those relationships. We published a chapter in the book to talk about all the roadmap to understand the battery performance in electric and hybrid vehicle operations. And if you are interested, I think that's going to give you some prior knowledge 15 years ago already, how we're going to face those problems and how we can take a reasonable step to address them. So jump into today's arena, we talk about from physical models to data-driven approaches. I think that easily we can categorize all these approaches in 4 major categories. The classical physical models is still being heavily pursued today to understand how we can apply the physical principles to the battery system design and their performance. And so we can get a better understanding from the test results to improve our capability to design a better battery. But as I mentioned, those complexity involved in their underlying mechanism versus the observable phenomena is so complicated. And so we often have to rely both on the expert system as well as some advanced regression models in order to manage, verify, and also filter the data into some tangible results that we can use in the design of the battery and the system managements. And today, I think with the more computing power, the hybrid system that integrate all the above three, become close to reality. And so I think we are in that transition today to look at it, how to advance the technology through a better platform, more complicated system integration, as well as modeling and computation capability to enhance our knowledge progression, and so we can really handle the problem. And that certainly also reflect into the whole data flow, into the decision-making process. And so the physical model, the regression models, and expert system rules-based system and knowledges had to be integrated. And so today's hybrid system, taking all the artificial intelligence approaches and data-driven capability, I think is making that become more and more into something that manageable. But we're still facing a significant challenges. And those challenges can be easily divided into two aspects. One is the data availability. The ability to acquire data through hardware and software integration has still remained as a significant barrier today. On the hardware side, both the resolution and sensitivity. On the software side, to have a good supporting infrastructure in order to manage the data flow, the data collection, as well as the data management, and how to apply the computational resources to accomplish those goals remain a very significant challenge, both on investments as well as the technology advancements. But another issue about the data quality has not been really tackled well enough to reflect the underlying problems that we are facing today. So both on the fidelity issues, whether the data collected will be sufficient to describe the system performance, and how we can verify and validate such results, is still quite in the infancy with all the advancement that we have developed so far. And so how to improve the data quality, it's going to be a daunting task in the future. And I think this has been discussed quite often now today in the literature. But one caveat is people still rely heavily with the standardized test approach. And with the test approach, I don't think we have a clear understanding about how to verify the fidelity and the accuracy and precisions for those measurements. And so this is the things I'm going to carry on in the second part of my talk. And I think that I hope will be clear at the end what kind of problem we are facing. So I think DeepSeek has been a very interesting topic for discussion recently in competing with OpenAI. And so the pro and cons between the two has been lively discussed in the media. I'm using a very simple concept. If you go to aquarium, the open AI probably is more into the ocean side, looking at all the informations that we can, reap from the ocean in the open environments. DeepSeek is probably more into the aquarium, that you want to find very refined details. Then you can easily extract the information with such a very concentrated experience. And so which one actually can give you the advantage in terms of cost, in terms of know-how and quality, which is something still quite missing today. It wasn't being clear. And with that, I still want to say all the heuristic approaches including physical models and data-driven approaches, I think we need to have very useful platform to truly validate and verify the results. And this is really the key for the quality. Okay. So the old saying say, well, if you want to have something cheap, fast, and good, you probably can only choose two. It's hard to come by a solution that can provide all three together. And so cheap and fast is something we're driven in the AI approach today. But I think to have something good with a good quality is something that's still missing. And we need to strive our resource more into this area. As my personal view, I think that really this is the largest challenges we are facing today. So, as I mentioned, the battery aging and degradation are path dependent. And this is not just a postulation. It's actually been found both in the candle life studies and cycle life studies in the past 2 decades. And we found those path dependence is really the most troubling aspect of the model and simulation efforts. And what's the root cause of the path dependence? It's not really clear. And I don't think that there's enough resource today being invested to understand the dependence. And so I want to raise that the sensitivity and to draw your attention. Those path dependent has very significant impact into the quality of the data and whether we really can overcome those barrier truly depend on how much we understand the origin of the path dependence. So some of the gestures we have today in terms of how to address those path dependence, very often we using this multifactorial and multi-scale effects in the kinetics to explain all this temporal dependence of the results is actually difficult to track. And in the simply put about this origin, I will just say, if we understand the physics good enough, the impact from all the environmental effects affect the battery performance. There's always a very complicated time constant associated with the kinetic involved. And so if we don't do the right data filtering and analysis, those temporal dependence will be the major source of those so-called path dependence, because things haven't been settled down yet, and we already try to develop implication about the message that the data try to reflect. And so those transient effects very often will create a lot of bias and uncertainties that we don't know how to characterize today. And this is really the underlying problems for the standardized test protocols, because that how much can create with the bias and uncertainties is not well characterized today. And this is really the nightmare for all the AI approaches, because such dependence will create a lot of difficulty in the regression and simulation, and even creating bias in the expert systems. And so we really cannot see the true quality of the data and how that can be reflected in the situation awareness. And so whether the algorithm or the model that we develop can truly reflect that is a big question mark. And to address that, I want to say this: we still have to go back to the fundamentals. Both the thermodynamics and kinetic principles need to be applied to validate and verify all these results. And those results, until it's really verified, otherwise the bias and uncertainties is still unknown, and we still don't know how much that's going to impact the accuracy and the precision of the prediction. And so in the follow-on slides, I'm going to show you some examples how we can use a well-established thermodynamic frameworks and kinetic framework to help us understand what the data and the analysis can tell about such issues. So the first example I want to show you is a recent paper we published regarding how to track lithium inventory in the battery system. And traditionally, people using GITT, the galvanostatic intermittent titration techniques, to get those informations, both for the thermodynamic relationship between the voltage and the composition in the well-defined framework, as well as all this diffusion coefficients and so forth, to validate their model through a better parameterization. But whether that results from the model and the experiments that echo each other is a good validation or not, I think is still remain as a very difficult task for us to verify. And I think this is something that we need to strive for very seriously in the future, is how to develop a really consistent platform so we can continue to filter the data and also verify the data quality in order to give a truthful response in terms of what system is reacting to the demand. And so this is the first example I want to show you. And how does that really works in terms of reality is we have to understand all the data we collected through a measurements really at the tap of the electrode. It's not at the interface between the electrode and the electrolyte interface. And so the earlier example I show you how we can reconcile the charging discharging behaviors. Very often they have discrepancies, even under so-called equivalent conditions, can be reconciled to show they are consistently show that unified, very universal relationship can be obtained. Same as here, this inventory tracking techniques actually help us derive the correct relationship of the potential during any test conditions at the interface. And I cannot explain in details, but I think easy to refer you to the paper to understand how we can remove all this polarization resistance so we can truly understand the electrochemical potential at the interface. It's very important. And this will become universal once you can get all kind of test results, whether they under the same test conditions or in the real life, you'll be able to consistently evaluate those results on the very reliable basis. And I think that this is the most important aspect I want to mention. And this can be applied to study aging as well as all this capacity retention issues that we already doing in the traditional model simulation and evaluation process. And this is really important to show not only you can evaluate a good data, but also you can evaluate data that doesn't show any rationalization in terms of what you want in the real physical process, but it actually happened in reality. And so I think that this is very important to apply this kind of framework to evaluate all the data, and the benefit is we can actually understand where all these variations come from and how we can address them. And so with that, I think that these techniques not only trace cycle by cycle all the capacity variation in different cells, but also they can evaluate the stoichiometric changes of the electrode, so-called lithium inventory tracing in the electrodes, cycle by cycle. And we know how those variations can affect the utilization of the materials. And so the kinetic degradations both can be traced, not just only the thermodynamic materials loss, but also the kinetic hindrance can be addressed very well. And at the end, we can see all the lithium inventory tracing can be quantified in terms of how much lithium inventories actually come from cathode and how much has come from the lithium anode in the lithium metal batteries in this case. And some systems actually can perform quite well. And there's a reason ahead to that, and that can be easily quantified through the analysis. And if we summarize those inventory tracing, we can find out the standard test protocol, so-called the end-of-life conditions, is not really well defined. And so I think this is a good example to show you how the new techniques in the analysis actually can help us decipher what really happened in the cell versus is just numerically looking at the test data without knowing whether underlying mechanism has been changed or not. And I think this is a very important message I want to share with you. And then you can easily using the same technique now to validate whether the inference from the electrodes, particularly in this case, when you use lithium metal as the anode, how the lithium morphology evolution actually can begin to reflect in the cycle life can be easily understand as well as quantified. So this is one example I want to show this. There's certain investments in the analysis can help us really quantify and validate all these variations from cell to cell. And so we don't have to rely on just statistical analysis to tell us the confidence level of the data in terms of quality. We actually can deep dive into the variations from cell to cell to understand where all these variations come from. Another example I want to show is even with the kinetic that creates such a complexity in the performance, we still can use very good kinetic framework to analyze data and try to understand all these variations. Is that really truly has physical meaning behind it or not? And so I'm using an example from the data has been published in a paper that is a well-known paper in Nature Energy, reported by the team from Stanford and MIT. They're looking at the data-driven prediction of battery cycle life in the early stage before a true degradation will happen. And as you can see, the accuracy of such approach roughly give you about 10% of errors overall. And we use in the same set of data, we actually go deep dive into the analysis itself and try to find out where all those problems may come from. Okay, so a very simple kinetic framework we use is just a very simple mechanistic model based on natural law of degradation. And we know in those cells, typically you have lithium inventory loss as well as active materials loss. And with that, we just simply use a simple natural degradation law expression in the mathematics and try to get a clarity to see whether we can just use those simple classic approach to analyze parameters and try to understand all these variations may come from each cells, how they're going to impact the accuracy and precision of the model prediction. So how good is this very simple classical model? We found this, they were actually quite accurate. The error is less than 0.5% for all the cells that has been reported in the paper. And they really represent very broad range of test conditions. And so their cycle life vary from 150 cycle to well over 2,000 cycles. And so with that kind of accuracy, I think that we actually found a very useful platform to understand where all these different algorithms that we can use both on the physical models versus the data-driven approaches. Can we begin to find out why different model and algorithm has limitation in their predictions? So in this case, I just want to show you this very simple physical models can give you very simple parameters. One representing the lithium inventory loss, and one representing the active material loss in the electrode. And with that, I think we can begin to see the lithium inventory loss has a very large pre-exponential constant, but very small value in their exponential factors. On the other hand, the inventory, the lithium active material loss has a much larger pre-exponential term constants, but the exponential factor is much it's much smaller in the pre-exponential constant, but the exponential factor is much larger than lithium inventory loss. So if you're doing the testing, what you're going to see is there's going to be a primary degradation from the lithium inventory as reported in the literature, but actually the most important factor is the active materials loss, which dominate the cycle life, which I'm going to show you. But first I want to say is you can use different regression methods, no matter it's a linear regression or it's a tree-based decision-making models. We can actually evaluate the sense of data and to see where all this accommodation of data variations and techniques such as data transformation as well as different model algorithm can give you what kind of predictions. And as you can see, the linear regression usually doesn't give you a very good results. Doesn't mean that it doesn't work. It's a problem is the limited sets of data actually has some drawbacks in applying the linear regression method, no matter how complicated you can transform the data to avoid some of the issues. But the tree-based algorithms actually can give you a much better results. But even that, compared to what we understand from the classical model, I think we can draw some very interesting conclusion here. So I think the key challenging in the AI approaches, a lot of time we need to adopt this uncontrolled sporadic operating condition and how that condition impact the test results. And this relationship is not really usually well understood. And so without understanding that correlations between the dependence variables to the independent test result that we develop through tests, there are going to be some bias and uncertainties involved in the data computation. And so how to assure the accuracy and precision, I think that this is really important to understand how the test condition and the test protocol will affect the quality of the data. And this is something haven't been addressed very well in the standardized test protocols that we practice today. And so with that, I think we know all these data-driven approaches will be sensitive to the sample size, data distribution, the dependency, or the correlations between the variables, and some other issues in terms of whether the data distribution variance is conform or non-conform to certain aspect of the data through the data acquisition process, as well as I mentioned about the bias, because the path dependent issues and many other issues, no matter the human induced errors or the system induced variations that we don't know where those uncertainty come from. I think those are the contributions that we need to really understand well enough in order to get a better understanding how reliable the results from the data-driven approach can be. And so, as we can see, the data distribution in the early stage is much more affected by the condition of the test, as you can see here. As cell degrades, as I mentioned, the cycle life is actually more controlled by the secondary factors, not the primary. So the lithium inventory loss is a primary, and that has much more scattering in their data distribution because the test condition is very sensitive, sensitively impact the test results. And so we don't really have ability to use those kind of data to determine cycle life. On the other hand, as you can see, the loss of active materials actually follow very well with a natural degradation process. And that actually is the one determining the cycle life at the end. But as I said, the secondary factors is difficult to detect in the early stage of the cell degradation. And therefore, there's not a practical way to understand how we can assess the cycle life at the end through the early data collection. But if we begin to look at more carefully in terms of whether the data is correlated between the two contribution of the capacity phase, we begin to see both lithium inventory loss and active inventory loss is actually well correlated in their relationship. And this is something that we usually don't have chance to find out just through the empirical approach of just looking at the data itself. And so from there, we can begin to see how these parameters being affected sensitively by the test conditions. And we can actually begin to look at all these conditions to see whether some of the cell has going through some abusive conditions. Sometimes we think the test condition is benign, but whether the abusive condition or the benign condition can affect the cycle life, it wasn't really true as we believe, which means the cycle life and the early stage of the test conditions that indicate whether it's abusive or it's benign doesn't really have a true correlations. And with that, I think that this is very important to see this example to show why the data-driven approach had to be carefully validated and analyzed in order to get a truthful results. And so I think I want to give you some takeaways from this talk. I think validations just between the model simulation and the physical model parameterization to correlate the simulation results with the actual data through any kind of correlations might not be truthfully reflect the data quality. And so the physics-based models actually can give us a better theoretical framework to deal with the verification and validations. Another aspect I want to mention is traditionally, we're not trained to understand mass transport aspect as in much detail as thermodynamics. But mass transfer actually is the one that dominates all this energy transfer process. And so this vintage perspective is not really being portrayed well in the literature. And I think that's one of the reasons we cannot really fully utilize the data-driven approach, because the mass transport actually has a lot of variations that create bias and uncertainty in the data that actually can mislead us to a wrong conclusion of the results. So with that, I think the prospect for all these data-driven approaches, I want to say this: even though we much focus on the cost reduction and the acceleration of the technology developments, I think the quality of the data and the quality of the AI approach is need to be addressed carefully. Which means, if you look at simple example as I mentioned about the difference between the OpenAI and DeepSeek in terms of their approach, we also can look at so-called the GPS. Even though we can create a very complicated digital twin, without a well-coordinated results to pinpoint the locations of the differences, I don't think we can see the clarity of all the impact and the uncertainties that change the results in the prediction of the model. And so I hope my talk will actually give you enough aspect in terms of how we can change this dynamics in the future in the AI approach in this field. And finally, I want to thank a lot of early work in Hawaii as well as later work in Idaho National Labs, and colleague has been working with me. They have been contributing a lot to the understanding of this aspect. So thank you for your attention.
Thank you so very much, Boryann, for that fantastic talk to open day 2 of Advances in Battery Research 2025. We really do appreciate you sharing your expertise with us today. We are likely to have lots of questions submitted during the Q&A session, and I can see that we have received some already, but I am aware of the time, so I believe we have time for potentially one question before we close out this session. So, Boryann, what kind of data is needed to support the AI approaches in battery technology development?
I think this is a very difficult question. As I show, if we have a good validations, the data to construct a reliable model doesn't have to be enormous. But the question is how to sieve and filter data so we can quickly reflect the true foundation of any data stream that coming out from the system, so we can eliminate all this bias, because the detecting issues, the data acquisition issues, as well as the bandwidth associated with the data collection and so forth. We need to streamline the process, but we need to have a very good framework to validate them. And so I hope my talk is really talk about the validation part. But the amount of data required, in my view, doesn't have to be so much to build the model. But the robustness of the model need to be withstand all this data stream, but we need to know how to filter data, how to select the right data, also try to remove all the noises come from human and system errors is really the key. And I don't think we have addressed that enough today.
Thank you so much, Dr. Liaw. Unfortunately, that is all that we have time for today, but thank you once again for such a fascinating session. Just a quick reminder to our audience, I'm aware we couldn't get through all of the questions today, but any questions that we didn't have time to get to will be sent to the speaker after the event. So that just leaves me to say a massive thank you once again to Dr. Liaw and to everyone in the audience. We'll be back soon with the next talk.
Before I leave, I just want to say is, some question I see here, I will try to answer them through the platform, or if you can send me your emails with your question, I can easily reply them through the email. And thank you everybody for your attention. Thanks.